Alright guys, today we're talking about classifying conic sections when we're given that equation in general form. And it's actually as easy as following a flowchart. So when we're classifying our conics, the first thing we want to look at when they're given them to us in that big general form is to how many of our variables are being squared. If you've got x equals y squared or y equals x squared, and if only one of the two variables is squared, it's guaranteed to be a parabola. Okay, so that's usually the first one to identify. If only one of our two variables is squared, it's a parabola. Now, if both variables are squared, the next easiest to identify is, do my two squared variables have opposite signs? Is one positive and one negative? Like x squared minus y squared, or y squared minus x squared, right? If only one's positive and one's negative, it's guaranteed to be a hyperbola. However, if both of my variables are squared and they have the same signs, then we're going to look at the coefficients. So if you have an equal number of coefficients, like 1x squared plus 1y squared, then it's guaranteed to be a circle. But that could likewise also be negative 4x squared minus 4y squared. They're the same sign and the same value. This is still going to be a circle. Okay, for an ellipse, we're going to have different coefficients. They're both going to be positive, or at least have the same signs and both be squared. But for an ellipse, we might have 4x squared plus 9y squared, right? Those coefficients will be different. Or negative x squared minus 4y squared. Again, here the fact that they're both negative doesn't mean it's a hyperbola, right? But we may need to divide both sides of our equation by -1 in the end. Same thing for a circle. So they should be the same signs, both squared, and different coefficients for an ellipse, the same coefficients for a circle. And you can think of those coefficients as kind of being the length of the major and minor axes, right, for an ellipse. If those are the same, you don't get an elongated ellipse, you would get a circle. Okay, so here's a bunch of examples, and we're going to use our flowchart to classify these very quickly. So classify each conic section. First thing I notice in number 1, I see both x and y are squared, so we can rule out parabola. And they're both the same signs, so we can rule out hyperbola. Then we look at, do they have the same or different coefficients? Well, 49 and 1 are very different. This must be an ellipse. Okay, number 2. Let's see, both variables are squared, not a parabola. They're the same signs, not a hyperbola. But my coefficients are exactly the same, which means in this case, this is a circle. For number 3, both variables are squared, not a parabola. This time, though, they have opposite signs. One is positive, one is negative. That guarantees hyperbola. For number 4, notice this time only x is squared, y is not squared. And if only one of your variables is squared, this is a parabola. For number 5, let's see, both variables are squared, not a parabola. Opposite, no, actually they are the same signs, right? They're both negative, but that is the same sign. So it's not a hyperbola. And my coefficients are actually the same. -1 and -1 makes this a circle. For number 6, let's see, both variables are squared, not a parabola. And they have opposite signs. One's positive, one's negative. This must be a hyperbola. Okay, try these last two out, see if you can figure out what those remaining ones are using your flowchart. I'll put the answer up in a second. All right, those last two were an ellipse and a parabola. Okay, since this section is relatively easy from there, we're going to go ahead and review some things like how can I write the standard form for each of our 4 conic sections given, say, a graph. So we'll need to know the standard form for each of these, so we'll have to rewrite as we go along. So number 9 is clearly a circle. So let's go ahead and write our standard form. Okay, so you might note or remember from a circle that we really just need 3 values. We need h and k, which are the coordinates of the center, and the length of the radius, which needs to be squared in our formula. Okay, so our center here is at 1, -3, and the length of my radius to any of these up, down, left, or right, until I reach an edge, is 2 units on our scale here. So plugging in, remember that our h and k should look the opposite of what they look like. So this should be x minus 1 squared, and then y plus 3 squared equals the radius squared. So if the radius is 2, this should say equals 4. Okay, next up we have an upward opening parabola. So let's make sure we start with that general formula. Okay, and then in this form, remember we need to know, again, in this case, the h and k are the coordinates of the vertex, which is here, and a is our vertical stretch, right? So we can calculate a using another point. So let's first, though, identify and plug in h and k. Okay, so h and k here are 6 and -1. So remember, h inside of here will look like the opposite sign, and k stays the same. It's not inside a parentheses squared here. Now we still need to solve for a, and the easiest way to do that is to pick any other point on this parabola. So we could use maybe 5, 1, or 7, and 1. Both appear to be nice integer points. Let's use 5, 1. And that gives me an x and y value that we can substitute in for x and y and solve for a. Okay, so substituting in 1 for y and 5 for x, let's go ahead and simplify everything over here. Okay, so subtract 5 minus 6 is -1. Squaring that is 1. 1 times a is 1a minus 1. Of course, 1a is just a. Add your 1 over, and we figure out that a for this graph is 2. So plugging that in with our h and k value from before, we get y equals 2 times, okay, which means typically what we would call c, right? The larger value should go underneath x here. So we need the coordinates of the center, h and k, which it looks like we can identify as being right here, which is, again, 1, -3, just a coincidence there. Okay, so we can plug in for h and k, again, opposite signs of what they look like. Now c, which is our major axis, was really the length from the center to the edge here. Okay, so that distance is 5 units. So underneath c, we should have 25. Sorry, underneath x should be 25. Okay, likewise, our a value here is in the vertical direction, and that is 2 units in length. So that is the value of a, and a squared is 4. So there we go, we've got everything plugged in. Here is the equation of our ellipse in standard form. Okay, let's take a look at our last one, the hyperbola. So in this case, it does matter which way it's opening. Because it's opening up and down, y will be our positive value. Okay, so for this, we need to know 4 values. The coordinates of our center, which are at h and k. Remember that k goes with y, h goes with x. And then our values of a and b. And a is always the distance from the center to the vertex. Okay, so we could do this up or down, but that distance here will be 3. Okay, and then b is the length horizontally, in this case underneath x, so it goes with x, from the center to the edge of this rectangle, right, which contains our asymptotes. So our b value is going to equal 1, and our a value is going to equal 3. Now the exact center here is the coordinates -4, -2. So those are our values for h and k. So now let's plug it all in. Okay, and there's our answer. We should have y plus 2 squared, right, opposite sign, minus, and then x plus 4, right, opposite sign squared. Remember that a squared, in this case is going under 9, it's the vertical distance to my vertex, and then b squared, 1 squared, is just 1. Okay, that's it. We'll go over more questions like this and go over that flowchart again, any questions you have, and then use that time to review for your test next class.